everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to look at the basicity of amines in terms of proton acceptance by the nitrogen lone pair and the reactions of amines with dilute acids, so for example hydrochloric acid, to form salts. Then we're going to look at the preparation of aliphatic amines by substitution of haloalkanes with excess ethanolic, ammonia and amines, and also the preparation of aromatic amines by reduction of nitroarenes using tin and concentrated hydrochloric acid. Now we're going to have a look at amines. So amines are another homologous series and they have the general formula of R and then NH2. So R is an alkyl group and then we have NH2. And they are thought to be derivatives of ammonia, just meaning that they've been made basically from ammonia. And what's different is that one of the hydrogens is replaced by an alkyl or an aryl, which is a benzene group. And we can get primary, secondary, and tertiary amines. So it's very similar to when we looked at primary, secondary, and tertiary alcohols. And to classify amines, we look at how many R groups are attached to the nitrogen. So what we have is first we have ammonia. So ammonia is NH3. So we have nitrogen with 3 hydrogens attached, and there's also 2 electrons, well, 1 lone pair of electrons on the nitrogen. And so this is ammonia. And then we have a primary amine. So that's where we have nitrogen and then 1 R group and the other 2 are still hydrogens. And so this is a primary amine. And again, we have the lone pair of electrons. And then we have the secondary. So this is where we have 2 R groups and a hydrogen. So this is a secondary amine. And then we have the tertiary amine where we have 3 R groups attached to this nitrogen. And amines are very reactive compounds, and so they're really good intermediates in synthetic routes. And what that means is that they're very good at acting as the intermediate. So we form it in the middle of a reaction in order to form different functional groups that we want to get. And primary aliphatic amines can be prepared by the reaction of ammonia with haloalkanes and by the reduction of nitriles. And now remember that aliphatic means non-aromatic. So basically any molecules that don't have a benzene ring. So like all amines, so basically made of carbon and hydrogen in straight chains or branch chains or cyclic, just not aromatic. And aromatic amines, so ones which have the benzene group, can be prepared by the reduction of nitro compounds and are used in the manufacture of dyes. And now we're going to look at naming. So with primary amines, we use the suffix amine. So for example, we have CH3, NH2. So how we would name this is, because it's a primary amine, we have amine at the end. And then we have a look at what this group is. And this is a methyl. And so the name of this would be methylamine. So the amine takes priority and the CH3 becomes a substituent group. And so similarly, we have ethylamine, which would have this formula. And we can also get one with a benzene. So we have benzene here, and if we have an NH2 attached here, this would be phenylamine, because again, the amine takes priority, and so it becomes the root of the name. With secondary and tertiary amines, we first name the longest carbon chain, and then place the name of the shorter alkyl or aryl group in front. And so, for example, we could have N that's attached to hydrogen, and then we have 2 methyl groups. So this would be called dimethylamine. Because the amine takes highest importance, and we have 2 of these methyl groups, and so that's why we use the prefix di. And then we could also get a nitrogen with a hydrogen and a methyl and also an ethyl. And what we would do here is first we need the longest chain. So the longest chain would be this ethyl here because it's got 2 carbons. And so that's what goes with the amine. And so this would be methyl ethyl amine. So this bit here is the longest chain we have. And so we treat this methyl as a substituent. So now we're going to look at the formation of primary aliphatic amines. So again, aliphatic just means non-aromatic, so amines that don't have a benzene ring. So when ammonia reacts with a haloalkane, it acts as a nucleophile. And this is due to the lone pair of electrons on the nitrogen, and so we have nucleophilic substitution occurring. And we can form primary aliphatic amines from this reaction. Now, we've actually already seen this reaction before in the haloalkanes chapter when we looked at nucleophilic substitution of haloalkanes. So I'm just going to revisit it very quickly. So the example I'm going to use is the reaction between ammonia and chloroethane. So the reagent we're using is ammonia, and the nucleophile is also ammonia. So we're going to start off with chloroethane. So that's going to be CH3, and then CH2Cl. And again, remember that we have partial charges because chlorine is a lot more electronegative than carbon. So chlorine gets a partially negative charge, whereas the carbon will get a partially positive charge. And now we have the nucleophile, which is attacking. So we have ammonia, and that's NH3. And we also have the lone pair of electrons on the nitrogen. And it's because of these 2 electrons that ammonia can act as a nucleophile because it's attracted to the partially positive carbon, and so it attacks that carbon. And then because we have incoming electrons, the electrons from this covalent bond feel a repulsion and move towards the chlorine, and this is how we get rid of the chlorine. So what we form is CH3, CH2, and then NH3. So we've substituted the chlorine for this ammonia. And we also form Cl- because that's what we've taken out because the electrons have moved towards this chlorine to make it negatively charged. And now something really important to remember is that because the nitrogen has donated electrons to the carbon to form a covalent bond, it is now positively charged. A really important thing to remember about these nucleophilic substitutions with ammonia is that we actually have another ammonia nucleophile which attacks. And so a second ammonia is then attracted to the positive nitrogen. And so here we have the second ammonia, again with the 2 electrons ready to form a covalent bond. And what it does is that it attacks this hydrogen, which is attached to the positive nitrogen. And then what happens is that these electrons from this covalent bond then move towards the positive nitrogen. And so now we can form the primary aliphatic amine. So what we get is CH3, and then CH2, and then we have NH2. And then the ammonia that's just come in, so this second nucleophile, has bonded with the hydrogen which has left the intermediate that we had. That's become an NH4+. And so this NH4+ then reacts with Cl- to form NH4Cl. So this has come from the NH4+ reacting with the Cl-. And then what we need to know is that this amine, which is formed, this primary amine, also has 2 electrons on the nitrogen, which are available to form a covalent bond with something. And so we have one lone pair of electrons on the nitrogen. And this is ethylamine. We call it ethylamine because the amine takes priority, and then we have a CH3CH2 group which is attached. So this is the substituent group, and it's eth because we have 2 carbons. Now we're going to talk about further substitution. So we've just seen that ammonia acts as a nucleophile in the reaction with haloalkanes to form a primary aliphatic amine. However, we can also get further substitutions. And so first what happens is that we can form secondary amines from a further substitution. So because of the lone pair of electrons on the nitrogen, the primary amine produced from the reaction of ammonia with haloalkanes can also act as a nucleophile. And so it attacks an electron-deficient carbon atom in another haloalkane. So we're going to look back at our example that we used for ammonia. So we reacted ammonia and chloroethane together to form ethylamine. And so now we're going to look at the reaction between ethylamine and chloroethane. So this is a further substitution. So what we have is that we have another chloroethane, so CH3, and then CH2Cl. And again we have the partial charges on carbon and chlorine. And now the nucleophile, instead of it being ammonia, it's now the ethylamine that we produced in the reaction with ammonia. So we have a nitrogen with a hydrogen, and then an ethyl group, so CH2CH3, and then a hydrogen. And remember that we've got this lone pair of electrons on the nitrogen, and this is what allows it to act as a nucleophile like ammonia is. And so these electrons are attracted to this partially positive carbon, and so move towards it. And then electrons from this covalent bond then move towards the chlorine. So again, we form this intermediate where we have CH3 and then CH2. And then we've substituted the chlorine out for this ethylamine. So we have a nitrogen with 2 hydrogens and then the ethyl group. And of course, we have this Cl- ion again because electrons have moved towards the chlorine and removed it. And so it's become a negative ion. And we also need to remember that this nitrogen is now positively charged because we've given away electrons to form this covalent bond with carbon. And then what happens is that we have another nucleophile come in, just like how we had with the ammonia reaction. But this time the nucleophile is ammonia. So these further substitutions happen when we have a mixture. So we've reacted the ammonia with the haloalkane, and then we've produced a primary amine. But then we've got some ammonia left, and so that's how we can use it as a nucleophile here. So we have 2 electrons on the nitrogen, and so what happens is that these 2 electrons attack the hydrogen which is attached onto the positive nitrogen, and then electrons from this covalent bond then move towards this positive nitrogen. So now we form a secondary amine. So what we get is CH3 and then CH2, and then we've got the nitrogen with the hydrogen and the CH2CH3 group. And again, we've got an NH4 plus ion and a chloride ion, and so they react together to form NH4Cl. So what we formed here is diethylamine. And that's because we've got 2 ethyl groups on the nitrogen. And so we use the prefix di because we have 2 of them. And then we need to remember that this nitrogen also has a lone pair of electrons on it. So this is our secondary amine. And then what happens is that we get further substitutions where we can form tertiary amines. So the secondary amine, which is formed from the previous reaction, also has a lone pair of electrons on the nitrogen, and so that means that it can also act as a nucleophile. And this is the key point, is that every time we produce something, the nitrogen still has that lone pair of electrons, and so we can get further nucleophilic substitutions. So again, we have chloroethane. So we have CH3, CH2, and then Cl. And remember, we always have to have the partial charges in. So the partial positive and the partial negative due to the electronegativity difference between carbon and chlorine. And then this time the nucleophile is this diethylamine. So we have a nitrogen with two of these ethyl groups. And then one hydrogen. And the key thing is that we have this electron pair, this lone pair here. And so it's attracted to the carbon and so moves towards it. And then these two electrons from this bond move towards the chlorine due to some repulsion. So what we form is CH3, CH2, and now we've substituted out the chlorine for this diethylamine. So we have a nitrogen with an ethyl group, and then another ethyl group, and also a hydrogen. And again, we form this Cl minus. So another thing that we need to remember is the positive charge on the nitrogen, because we've donated the electrons to the carbon to form that covalent bond with it. And again, we have an ammonia nucleophile attacking. So we have NH3. And again, these two electrons target the hydrogen, which is attached to the positive nitrogen, so this one. And then these two electrons move towards this positive nitrogen because they're attracted to that positive charge. And so now we form the tertiary amine. What we get is CH3, and then CH2, and then we have nitrogen with two ethyl groups on it. And again, the NH4 plus formed from this bit here, from the hydrogen, the nitrogen donating the electrons to the hydrogen to form a bond with it. That NH4 plus reacts with the Cl minus to form NH4Cl. So this is triethylamine, because now we have three ethyl groups on it, on the nitrogen. So this is our tertiary amine. And then what happens is we get one last substitution, and we form what we call quaternary ammonium salts. So we know that ammonia can only bond 3 times, and then it has a lone pair here. And what it can do is donate this lone pair to something else, and this will form a salt because it will have a charge, it'll be positive. And so what we have is that, again, we have chloroethane. So I'm going to write it CH3 and then chlorine on the end. Again, remembering the partial charges, so we've got partially positive and a partially negative. And then this time the nucleophile is this triethylamine. So we've got nitrogen with 3 ethyl groups on it. Because it's a tertiary amine. And then the lone pair of electrons. And again, they target this electron deficient carbon. And then these electrons from this covalent bond feel some repulsion and move towards the chlorine. And then we form CH3, and then CH2, and then N, and now we have 3 of these ethyl groups on it. And then also the chloride. And now we need to remember again that this nitrogen is positively charged because it's lost some electrons. And so now we don't get another ammonia attacking as a nucleophile because there's no more hydrogens left on this nitrogen to be substituted out. And so what happens is that these two ions produced then react together to form this quaternary ammonium salt. So this bit here is our quaternary ammonium salt, and how we write it is CH2, CH3, 4, and then the nitrogen, which is a plus, and then Cl, which is a minus. So this is our quaternary ammonium salt. And in this case, what we would call this salt would be triethyl ammonium. So this is what we get from the positive bit, and then chloride. So really important things to remember are that these are all nucleophilic substitution reactions. And that's because the attacking group is always a nucleophile, which has a lone pair of electrons available to donate to something else to form a covalent bond. And we're substituting the chlorine for the nucleophiles, and so it's a substitution reaction. And another thing we need to remember is that the reason why all of these further substitutions happen is because the products that we form always have an electron pair, a lone pair of electrons on the nitrogen, which means that the product can act as a nucleophile. So first our nucleophile is ammonia, and then the primary amine which we have formed also has that lone pair of electrons on the nitrogen, so that can also act as a nucleophile. And that's the same with then a secondary amine, and then finally a tertiary amine. And so we can go all the way to forming quaternary ammonium salt. Now we're going to look at the different conditions for this reaction of ammonia with haloalkanes that we can have. So we know that when we react ammonia with a haloalkane, we get a mixture of primary, secondary, and tertiary amines, and also a quaternary ammonium salt. And because of this, it isn't a good way of preparing primary amines. And so the general rules are that if we want a high yield of primary amine, we need to use an excess of ammonia. Or alternatively, we could have a limited amount of haloalkanes. And this is because this prevents further substitution. Because if we don't have very much haloalkane, or if we have a lot of ammonia, and that's all, ammonia is the only nucleophile that will be reacting with the haloalkane, and so only a very high yield of primary amine will be formed and not as much further substitution. However, if we want to obtain a mixture of amines and the quaternary ammonium salt, we need to use an excess of the haloalkane or a limited amount of ammonia. So this kind of question comes up quite a lot in exams. So just make sure that you understand why, if we want a high yield of primary amine, we need an excess of ammonia, and why, if we want to obtain a mixture of amines, that we have an excess of the haloalkane. So the reason why we need to have an excess of haloalkane to obtain a mixture is because we want loads of further substitutions to happen. And that can only happen if we've got lots and lots of haloalkane react with the different nucleophiles that we produce. Now we're going to look at the reduction of nitrile compounds. So another way we can prepare primary aliphatic amines is by using a two-step process starting from a haloalkane. And this is the most common method used to form a primary amine, as the only product is a primary amine. And this is instead of a mixture of amines and a quaternary ammonium salt. And so this means that the overall yield of primary amine should be 100% theoretically. And this is also a very useful reaction in organic synthesis, as the product has one more carbon atom than the starting haloalkane. So we're going to look at an example of making ethylamine. So this is the same example as the one we looked at for the reaction of ammonia with haloalkanes to form a primary amine. So it happens in two steps. The first step is nucleophilic substitution of the Cn- in aqueous ethanol. So the reagent we use is is potassium cyanide, and it's dissolved in aqueous warm ethanol. So because we're making ethylamine, we need a haloalkane to have one less carbon compared to this ethylamine, because the CN minus will add an extra carbon. And so we start off with something methane. So I'm just going to choose chlorine. So we have chloromethane, which is CH3Br. And then what happens is that we add potassium cyanide to provide the CN minus nucleophile. And then what we form is CH3, C triple bonded to an N. And so nucleophilic substitution has occurred. And then we get the Br minus, which has come from the bromomethane, but it reacts with the K plus ion from the potassium cyanide. And so we get potassium bromide forming. And then for step 2, we get hydrogenation with hydrogen and a nickel catalyst. And this is basically a reduction reaction. So we have this CH3, C triple bond. And so this will react with 2 hydrogens. And also this is using a nickel catalyst to form CH3, CH2, and then NH2. So this is the primary amine that we were looking for, this ethylamine. And how we write this using reduction notation is that we write CH3, C triple bond N plus 4 of these square bracket H's to form ethylamine. And so because ethylamine is the only product of this reaction, so these 2 steps, this is why this is most commonly used, because we don't get that mixture of amines and the salt. Now we're going to look at preparing primary aromatic amines. So we can produce primary aromatic amines by the reduction of nitro compounds using tin and concentrated hydrochloric acid. And this reaction forms ammonium salt, but we can add sodium hydroxide to obtain the amine. So our example is producing phenylamine. So what we start off with is nitrobenzene. So we have the benzene ring, and then we have a nitro group attached. So this is nitrobenzene. And what we can do is reduce this. So what happens is that we can add some reducing agent. So we can add 6 reducing agents to form our phenylamine. And we also form 2 waters. So what we're adding in this reaction is tin and hydrochloric acid. So tin will be the catalyst, and we're adding hydrochloric acid to it, and then followed by the sodium hydroxide. And this is our phenylamine. Now we're going to talk about amines as bases. So because amines have a lone pair of electrons on the nitrogen atom, they can act as weak bases, and we say that they have basic properties. The bond between the nitrogen and H plus ion from the acid is a dative covalent bond, as the 2 electrons in the covalent bond both originate from the nitrogen, so the lone pair on the nitrogen. So for example, we're going to look at general equations of amines acting as bases. So first, looking at primary amines, they have the structure R and then NH2. And so if we add an acid, so a H plus ion, what we form is R and then NH3. And now the nitrogen will be positively charged because we've given away some electrons to form a covalent bond. And so, for example, if we took R to be another hydrogen, what this would look like would be we'd have a nitrogen and then the original 3 hydrogens. So this is taking R to be equal to a hydrogen atom. And then we formed a dative covalent bond with another hydrogen. So we have this lone pair of electrons on the nitrogen, and they've been donated to this H plus to form a dative covalent bond with it. And so this would be the shape of it, and this would be a plus ion. And this would also be a tetrahedral shape, because instead of having the lone pair on the nitrogen now, we have a bond to the other hydrogen. And so this dative covalent bond is counted as a bonding pair. And so we now have equal repulsion from all of the pairs of electrons, because they're all bonding pairs. We have 4 bonding pairs, and so we have a tetrahedral shape. And we also will have an 109.5 degree. And now looking at secondary amines, we have 2 R groups this time, and we do exactly the same thing. So we add a H plus, and then we get R2 and then NH2. And again, there'll be a positive charge on the nitrogen because we've just given away some electrons to the H plus that we've added. And then for tertiary amines, we have 3 R groups, and then they're all attached to a nitrogen, and we add a H plus, and then we get R3NH. And again, there's a positive charge on the nitrogen. So if we look at a more specific example, we could look at ethylamine acting as a base. So ethylamine looks like this. We have a nitrogen, and then we have the ethyl group, so CH2, CH3, and then we have 2 hydrogens attached to this nitrogen. And then we have 2 of these electrons on the nitrogen, the lone pair. And then we're adding a H plus. And what happens is that these 2 electrons move to this H plus, this positive charge, because they're attracted to it. And so what we form is this ionic salt. So we have a dative covalent bond to the hydrogen, and then we still have the ethyl group and the other 2 hydrogens. But this time, the shape will be tetrahedral, and this will be a positive ion. And then we also have some Cl minus ions, because the acid that we're using is actually hydrochloric acid. And so we also form a Cl minus ion, because that hasn't actually done anything in the reaction. And we call this salt ethyl ammonium chloride. This is if we have the Cl minus and this ethyl ammonium salt. The next reaction we have to look at is the reaction with acids. So amines as bases react with acids to form ammonium salts in a neutralization reaction. And this is because the salt formed will be neutral. And the addition of sodium hydroxide to an ammonium salt will convert it back to the amine. The ionic salts formed in this reaction are soluble in the acid. So for example, phenylamine is not very soluble in water, but the ammonium salt, phenyl ammonium chloride, is soluble. And these ionic salts will be solid crystals if the water is evaporated, because of the strong ionic interactions that take a lot of energy to break, and so they'll be solid. So the example we're going to look at is methylamine reacting with some hydrochloric acid. So we have methylamine, which is CH3, and then NH2. And then we're going to react this with hydrochloric acid. So what we get is CH3, NH3 plus, and Cl minus. And what we call this salt is methyl ammonium chloride. However, for acids which are diprotic, so they give off 2 H pluses for every acid, we could have, for example, again this methylamine, but reacting with H2SO4 this time. What this means is that for every sulfuric acid we have to have 2 of these methylamines, because we can only provide one CH3NH3 plus ion for every methylamine we have. And so what we form is CH3NH3 plus, and we have two of these, and then we have the SO4 2 minus. And now the charges will balance out. So this is methyl ammonium sulfate.